Welcome back to my YouTube channel. So we are diving straight to another section on partial differential equation. So in our last video we treated how to solve partial differential equation by direct integration, which is one of the simplest methods for solving partial differential equation. So now we're going to be looking at how to solve PDEs by separation of variable. So now the two basic form of equation we can apply separation of variable are the wave equation and the heat conduction equation for a uniform finite bar. So on this section of this video, I'll be taking the wave equation. So now we're going to be looking at how we can solve PDEs in form of wave equation. So now what is the wave equation? So let me write it out. So like I said, we're going to be considering the wave equation. So before I write the wave equation out, let me explain what the equation itself is all about. So now, for example, you're having a string, right? A string of length L. So this is your string right here. This is your string, right? It's having a distance from length L, right? So now, for example, you're having this type of string now from length L, and from 0 to this point here is L, right? This is point 0 and this is point L, such that your distance is L. So if I complete it to form a coordinate axis, right? This will be my y-axis and this will be my x-axis. So if I displace the string, if I hold this point, these 2 points fixed, this is a string, right? Just like a rubber band. So if I hold these 2 points fixed and I vibrate this string, so the maximum displacement, this string will be displaced, right? Yeah, string will be displaced. So now the maximum displacement I will get, let me call it u, which is a function of x and t, right? The displacement of the string is a function of the distance and the time. So where from here to here is my x. So now this is the total displacement of the string. So now the wave equation is trying to tell us that displacement of this string, the maximum displacement of this string is given by the equation, or we can get the maximum displacement of this string from the equation d square u over the x square is equal to 1 over c square du dt. So now this is what I call the wave equation. So with this partial differential equation, which is also known as the wave equation, I can get the maximum displacement of this string, right? So this is what I call the wave equation. So you can take note of this or you can note it down. So now, how can we solve this wave equation? So now this, we are having a second order differential equation, right? You're having a first order differential equation. Sorry, you're having second order 2 here. Wave equation, this is d square u over dt square. So this is d square u over the x square, and which is equal to 1 over c square d square u over dt square. Now where c itself is a constant. So now c can be defined as thermal conductivity divided by the specific heat of the material, then times the mass per unit length, which is irrelevant. Just know that c is a constant. So c can attain any value, can be 9, it can be 3, and so on and so forth. So now how can we solve this particular partial differential equation? So now there are steps to follow. I'm going to be outlining those steps one by one. So before we solve an actual solution or before we solve an actual problem, this video is going to be talking about only how to solve PDEs, the steps to follow on how to solve this particular PDE. So for example, the step 1 says we are going to assume this u we are looking for. We are going to assume it's a function of x and t, right? You know there's a function of x and t, right? So now let's denote it as capital X and capital T. Now this is my step 1. Now let's denote it as capital X and capital T. So now where my capital X itself is a function of small x and my t is a function of small t. Now these are mostly irrelevant. Don't worry, just follow me step by step. You know how to go about this. So now it's a very simple process. So now since u is a function of x and t, right, and x is a function of small x and t is a function of small x, so now let me differentiate it. Now I want to differentiate u with respect to x, right? I want to differentiate u with respect to x. Just like I want to get the form of this from this. So meaning I'm going to differentiate u 2 times, right? So differentiating u, the first one as du dx, right? I have, so since this is a function of x, right, I will differentiate it where t is constant, right? Remember, when I'm differentiating with respect to x, that means this t will be constant. So I'm differentiating t, I'll differentiate it once, right? That's x prime t, right? Then I'll differentiate it again, that's the square u over the x square, right? Then this is x prime prime t, where my t is constant, right? So now, let me differentiate u with respect to t, because I'm also having du dt here, also. So now, this is, let's call this a, right? So now let me differentiate u with respect to t. So that's differentiating it first, that's du dt. I have x t prime. Remember, where my x will be constant, right? I'm differentiating with respect to t, my x will be constant. Then differentiate it again, that's the square u over dt square. I'm having x t prime prime. This is the value. So my d square u over dt square is x t prime prime, and my d square u over the x square is x prime prime t. So now I'm going to be substituting these values I got. I'm going to be replacing the x square here and this t square here with these values I got here into the wave equation. So now let's do that. Substituting it inside the wave equation, right? So now the first thing, we express u as x and t, right? Then we substitute inside the wave, we differentiate. So we have to differentiate, right? Differentiate, right? Then now we want to substitute the values we got from the differentiation into the actual equation. So since the wave equation is given as d square u over the x square equals 1 over c square, d square u over the t square, right? Substituting this, we have x prime prime t equals 1 over c square dot x t prime prime. So now, this is where we apply separation of variable. So now, what are we trying to do here? Now we are going to separate the function of x for x and the function of t for t, which we call separation of variable. So this is how we solve this PDE, using separation of variable. So this is where we apply our separation of variable. So now, to get to make x to move towards the x side and to make t to move towards t, I'll just divide through by x and divide through by t. So now I'm taking x here. This is x prime prime over x t equals 1 over c square t prime prime. So taking t also towards this side, so I'm left with x prime prime over x equals 1 over c square t prime prime over t. So I've successfully separated the variables out, right? So now this is step 2. This is step 3, substitution, right? So now step 3 is substitution, step 4 is separation of variable, right? So now, after we've attained this form, so what do we do next? So now we're going to introduce a constant for both sides, meaning that for my left hand side, I'm going to introduce a constant k, which will also be equal to my right hand side. What am I trying to say? My left hand side is equal to x prime prime over x, right? Now I introduce a constant to it, which is I assume it to be equal to k, right? So now I also do the same too for my right hand side, which is 1 over c squared t prime prime over t. I equate it towards k, right? So now let's turn it into an equation, right? So this is x prime prime minus kx, right, is equal to 0, right? So this is my 5th step, right? Then do the same thing here. So this is t prime prime equals c square k, right? Taking this to this side, right? So this gives me this is c square kt. That's cross multiplying, right? So taking it to this side, so this is t prime prime minus c square kt equals 0, right? So the constant we assume, we are going to say let k be equal to minus p square. Now there's a reason why we are assuming k to be equal to minus p square, because when we test for k is equal to 0, it gives us the equation becomes non-oscillatory. Now what do I mean by non-oscillatory? Meaning that this particular equation here, when I solve this part, I can solve this using your normal ODE, right? This is like the s square over just like saying second order minus kx, right? I can solve this using normal differential equation, right? In which I'll have my solution to be a cos nx plus b sin nx. So now when I solve when k is equal to 0, the solution I get is equal to 0, and when it is equal to 0, it's non-oscillatory. So now I'm looking for a particular solution in which I'm not going, my two constants a and b is not going to be equal to 0, and that can only satisfy when k is equal to minus p square, right? So now I'm going to be substituting k. So for all the solution you are going to solve, now for all the solution you are going to solve, we assume k is equal to. So for this step I'm going to follow, you will not actually need to solve this particular step when you are solving an actual problem. You will just need to know that the solution of this is this and solution of this is this. So now substituting k is equal to minus p square here. So this is x prime prime minus p square x, right, equals 0, right? Do the same thing for this. So this is t square minus c square minus p square t equals 0, right? So this minus times minus is plus. So this minus times minus is plus. So this is k prime prime plus p square x equals 0, and this is t square plus c2 p2 equals what? 0. So now we're going to solve this using your norm, like I said, using your particle. So now remember, to solve this is just like your normal ODE, right? Ordinary differential equation. So now to solve this particular ordinary differential equation, remember this can be written as let's assume is the x square over the x square, right? Big X over small x plus p square. Then we assume this to be this is just ordinary x. Yes, this is just ordinary x. Remember, I can solve this. Remember, a particular to solve the differential equation of this form, the solution I'm going to get is equal to x is equal to a cos. Remember, this is p, right? So it's going to be a cos px plus b sine px. So just take note of this, that you are going to be using this same solution for your x throughout any problem that concerns wave equation and heat conduction. So now this is my 6 steps. I substitute k equals to minus p, right? Minus p square. And my 7th step, I find the solution of my differential equation, right? Which I have x is equals to a cos px plus b sine px. So the same thing that happens for my t side also. So I have to find the solution to this now. And the solution for my t also will be t is equal to let's assume a different constant, c cos. Now in this case, now the constant that is here, remember the constant that is here was p square, right? That's why we squaring p square, I have p. I'm going to take one of it. So the constant I'm having here is c square p square. So now I'm going to be taking cp. So c cos cp t, remember x is a function of small t, plus d sine cp t. Remember, if you want to know how I got this my solution to this ODE, you can check my solution to ODE videos, and I did mostly on how to get ODE when you're having a form of d square x square over x square plus. Remember, you can have different form of solution when you're having this particular form of ODE. So one of the forms, when it's plus, is a cos px plus b sine px. When it's plus 2 is also this. But I use a different constant because we are talking of different variable. This is a variable t and this is variable x. So now these are the two solutions you have to take note of when you are solving wave equation. So necessarily when you are solving a particular problem, you will not need to move. You will not need to apply step 6. You can just move from here, from step 5 to step 7, and write your stuff. So now what are we going to be doing now? So now, since remember we said u is equal to xt, right? So now we are going to bring these two equations together. So u is equal to now a cos px plus b sine px, right? Then times c cos cpt plus d sine cpt. Beautiful. So now we brought the two equations together, and this is what we are having. So now, what will be our next step? So now the next step in solving this particular this thing now. So now we're going to assume that let Cp be equal to lambda, where lambda is my eigenvalue. So this is my 8th step, bringing u and x together, and my 9th step is assume Cp to be equal to what? Lambda, right? So now, where my p now can be written as lambda over c, right? So I'm going to be substituting p into the equation for you. Now you see this now, you're also going to apply it when you're solving your normal problem. Remember, don't worry, after this video, I'll treat a problem on wave equation. So now let's assume p to be equal to lambda over c. So I'm going to substitute this now into my equation for you. Remember, this is my equation for you, right? I'm going to substitute p into this, right? So substituting p into this, I have what? So like I said, we're going to be substituting Cp equals lambda into the equation for u, right? So now let's where my p is equal to lambda over c, right? So now substituting this, we'll be having u is equal to a cos lambda over c x plus b sine lambda over c x, right? Then do the same thing too for this place. This is c cos c times, remember cp is lambda, right? So cp here is lambda, so this is lambda t plus d sine cp is lambda, right? So this is lambda t. So now this is step 8, right? So now, sorry, this is step 9. So now my next step right now, my next step now is to, so now what is my next step? Now there's what we call boundary condition and initial condition. So for when you're solving wave equation and the second equation, which is heat conduction equation, you are going to give in boundary condition. So now the boundary condition is, remember I said let's assume a length of string L, right, in which you have 0 to L, right? So now you're having this string 0 to L, right? In which where S, we now completed it to form a coordinate axis, right? So we said when x is equal to 0 and x is equal to L, it vibrates between x is equal to 0 and s equals to L, right? So now these two things here is my boundary condition. The boundary condition is the limit, the range at the two ends of the string. This is my boundary condition. So now for a particular wave equation, your boundary condition is going to look like this: u 0 t is equal to 0 and u L t is equal to 0. What is this trying to say? This is when x equals to 0 and when x equals to L. So they are trying to tell you that when s is equal to 0 and when s equals to 0, remember I said this is my maximum displacement, u, Abi, and u will be 0 at this point, right? At this point when x equals to 0, and u also be 0 at this point when s equals to L. So u is equal to 0 as x equals to 0 and u is equal to 0 at s equals to L. So this is my boundary condition. So now this is my boundary condition, right? So now you're also going to be having an initial condition. So your initial condition says that u at t is equal to 0. Remember this y here is a function of x and t. So at t is equal to 0, you'll be having a function x, right? And my initial velocity, before, let's assume a particle is moving along this line. So my initial velocity is du dt, where t is equal to 0. Remember initial velocity, before it starts moving, that before this time starts counting, my t is equal to 0, and it's given will also be given my initial velocity is always my initial velocity also assume a function x. Let's call it gx. So this right here is my initial condition. So you are going to be given these two types of boundary condition when you are solving wave equation. So now my 10th step now is to apply my boundary condition. So my initial condition is going to come later. So I apply my boundary condition. So my boundary condition, which is given as u when x is equal to 0, my u is equal to 0, or when x is equal to L, my u is also equal to 0. So I'm going to apply my boundary condition on my u. So now when x is equal to 0, right, I put x here. Remember this is a function of t, so the x only applies here. So I put x here. So now what do I have? So this is u a cos lambda over c times 0, right, plus b sine lambda over c times 0 also. Then this is c cos lambda t plus d sine lambda t. Remember I said when x equals to 0, u is equal to 0, so this is 0 itself, right? Remember 0 times this is 0, right? 0 times this is 0, so cos 0 is 1, so this is, we have a here. And 0 times this is 0, sine 0 is 0, so b times 0 is 0, so we have 0 here. And this is c cos lambda t plus d sine lambda t. So what do we do now? Since I'm looking for the value of my constant, I want to look for the value of a, right? So now I'm going to divide through by what I have here. Since I assume x is equal to 0, so it doesn't concern my function of t. So dividing through by this So right here, dividing through by this, so right here a is equal to 0, right? 0 times this is 0 divided by this is 0, so a is equal to 0. So I've gotten the value of my first constant, a is equal to 0. So I can write my u as, since a is equal to 0, so this is 0. So I can write u as 0 plus b sine pi lambda over c x cos c cos lambda t plus d sine lambda t. So what do I do next now? Is to apply my second boundary condition. Let's call it step 10b. Remember, my first boundary condition was this, right? Which I applied to have this. So I'm going to apply my second boundary condition, in which it says u, when x is equals to L, my u is also what? 0. So I'm going to apply it here too, right? So when x is equal to L, substituting L here, so this is my u is equal to 0, right? So this is 0 is equals to b sine lambda over cl, right? Dot, open bracket, cos pi t, you're not substituting anything here because this is a function of t. This is d lambda t. So now I'm dividing through by this here, dividing through by also this, dividing through by this. So my b sine lambda over cl is equal to what? 0, right? So now, if b, now we are going to, just like Sturm Liouville equation, we are going to choose the value that will make to be equal to 0. Remember, if we make b to be equal to 0, it becomes non-oscillatory. Remember, I said when the solution, remember this here is the solution for my x, right? If you can remember how we got it, this here is the solution for my x. Remember, if you have a to be equal to 0 and b to be equal to 0, if we are solving a Sturm Liouville equation, we say it is a trivial solution. But since we are solving a PDE, partial differential equation, wave equation, we say it's non-oscillatory. So now we will not want to make b to be equal to 0. So we will just say, okay, since b cannot be equal to 0, if not, it will be non-oscillatory. Let's make sine pi over cl to be equal to 0. So sine pi over cl to be equal to 0. So the only thing I can make sine pi over cl to be equal to 0 is when I'm having pi, right? Pi, which is 180. So any value of pi, any value of 180, I guess 180 times 2. Now let's test it. Let me explain what I mean. The only thing I can make sine to be equal to 0 is pi. Sine pi, that's sine 180 is 0. And also sine 2 pi, that's sine 360 is also equal to 0. Sine 3 pi is also equal to 0. Sine 4 pi is also equal to 0. So now, meaning that 1, 2, 3 pi makes sine to be equal to 0. So the only thing I can make this sine to be equal to 0 is only when this lambda over cl is equal to n pi, where n can be 1, 2, 3, 4, and so on and so forth. You understand now? So now I'm going to find the value of lambda. Lambda is equal to c n pi over l, right? This is my eigenvalue, right? So now, what do we do now is to substitute lambda back into my equation for you. Remember, we applied my second boundary condition to get lambda. I applied my first boundary condition to get the value of a, and I applied my second boundary condition to get the value of lambda. So now we substitute back to u, right? So this is my step 11. So u is equal to b sine c n pi over l, right? Divided by c x, right? Open bracket, cos lambda is c n pi over l t plus d sine c n pi over l t. C you can also see, right? So what are you left with? We are left with b sine n pi x over l, open bracket, c cos c n pi t over l plus d sine c n pi t over l. So this is my updated version for you. Remember, all what this solution is to calculate the value of u. How do we get the value of u? So now let's proceed. So now, since we have gotten the value of lambda, right? So now let's assume, since we are having n here, since we're having n here, meaning that we can have a series from this, right? What am I trying to say? Meaning that first thing, let me multiply. Let me say, let b times c be equal to c. Let's b times cp to be equal to cr, and let b times d to be equal to dr. I'm trying to introduce a new constant. Since we're having three different constants, and this can multiply this, and this can also multiply this. So if I multiply this times this, let me assume a new constant CR, or let me assume a new constant CR. Let me assume a new constant Cn, and b times let me assume a new constant Dn. Right. So now let's multiply through. So u can be written as sine n pi x over L, open bracket, Cn cos Cl, or cos Cn, that's C times n pi t over L, plus Dn sine C times n pi t over L. So this is my updated version. This is my updated formula for you, right? Sorry for that. This is my updated formula for you. So I just multiply this times this to have this, and this times this, that's this subscript n. So multiply this times this is BC, right? And BC I assuming to be C subscript n. This times this, that's BD, I assuming to be D subscript n. So now what do I need to do now? To make my solution for you, to make my solution for you to be equal to be authentic, I need to get the value of Cn and Dn, right? The normal way you have to get the value of the constant. So how do we get the value of the constant? First thing, I'm going to assume a series. I assume my u is a series. Since I'm having n, so I can say let n be equal to 1, then let n be equal to 2, and so on and so forth. So now let's do that. So now let's say let n be equal to 1, right? So I can say call this u1 is equal to sine pi x over L, right? Open bracket, c1 cos C pi over t over L, right? Plus d1 sine C pi t over L, right? Let n be equal to 2. I have u2 equals sine 2 pi x over L, right? Open bracket, c2 cos 2c. Remember, this is n here also, this is n here also. That's why I'm substituting 2 here. I'm substitute 2 here. So this is 2c pi t over L plus d2 sine 2c pi t over L. So now if you can keep going and going and going, you have a series. So now, and when you have a series, for example, you have a series solution for u, right? The total solution I get is going to be u is equal to u1 plus u2 and so on and so forth, right? This is the total solution I'm going to have for you, the summation of all my series, right? So now before we dive into that, this is my, which step are we? This is my 12th step, right? So now 12th step, that's substituting n equal to 1, and so now I'm going to be having a series. Now we can write you this formula for you. Since we are going to be having consecutive numbers 1, 2, 3, 4, and 5, let's assume u r, right, equals sine r pi x over L, open bracket, cr cos r c pi t over L plus d subscript r sine r c pi t over L. Right. What do I do today? Where r is equal to 1, 2, 3, and so on and so forth, right? Since we're having a series, just like when I put n equal to 1, I have u1 equals to this, n equal to 2, I have u2. So I just rewrote this as a general form for writing the series. So now, since you said the solution I'm going to have for my u is going to be summation of the consecutive numbers, right? Meaning that summation of ur, right? Summation of 1, 2, 3, 4, right? So now, meaning that u is going to be summation where r is equal to 1 to infinity of ur, right? Meaning that when u equals to 1, that's 1, 2, 3. I'm summing all the value of u1, u2, u3 to infinity, right? So now the solution for you I'm going to have is going to be this, right? So I can write this as you remember u is a function of x and t, right? So this is my 13th step, right? Write the general form for ur. So my 14th step now, since I'm summing this, right? U is summation of u where r is 1, 2, 3, and 4 and 4. So I just wrote this as the general form of this, which I wrote here, right? So now u, which is a function of x and t, can be written as summation start from r is equal to 1 to infinity. And remember, my ur is this, right? So my ur, substituting this for this, open bracket, sine r pi x over L, open bracket, cr cos RC pi t over L plus dr sine RC pi t over L. So now, in order to find, remember I said we need to find C subscript R and D subscript R. So how do we find C and D? It's very straightforward. Now, this is where our initial condition comes in. Remember I said we're going to apply our initial condition later on. So this is where our initial condition comes in. Remember our initial condition, we said x, and where t is equal to 0, that's where your time is equal to 0, assuming we have a function of x. Now this function of x you are given here, they are going to give you in the question. Remember, when you are given a question, they are going to give you your condition, your boundary, and your initial condition. And we also know that said the initial velocity and t is equal to 0 is equal to gx. So now I'm going to apply my boundary condition, right? So apply my first boundary condition, in which we said when x is equal to 0, you are having fx. So now I'm going to put I'm going to have t is equal to 0 here, right? Remember, where t is equal to 0, you have fx. So putting t is equal to 0, remember ux now will now be equal to fx, right? Remember, when I put t is equal to 0 here, this becomes fx, just like what the condition says, right? So the condition says when I put t here, this becomes fx, right? So this is equal to summation, start from r is equal to infinity. So this does nothing concern my sign r by x. Remember, I'm only substituting t is equal to 0, so nothing concern this. So I can assume this to be a constant. So this is sine r by x over L, open bracket, CR. So when I put t is equal to 0 for this one, right? Let me just write it out. This is called r c pi times 0 over L, right? Plus dr sine r c pi times 0 over L. So when I put 0 here, this is r c pi over L times 0, which is 0, right? And cos 0 is 1. But when I put 0 here, r c pi over L times 0 is 0, and sine 0 is 0. So automatically this becomes 0, right? So I'm only left with c subscript r. So I can write my fx to be equal to summation from r equals 1 to infinity, open bracket, sine r pi x over L, open bracket, cr, yeah, just cr. Remember, cos 0 is 1. So this is just left with cr, right? So now, this can be written as, remember, this is a constant, or you can just put them together. So this is summation, start from r equals 1 to infinity, cr sine r pi x over L. So now here we apply Fourier series. It's just not technically we are solving this as a Fourier series. We are just applying the principle of Fourier series. Remember, the principle of Fourier series, when you are giving, let's just assume this is a Fourier series of a function, right? This is a Fourier. Let's assume this is a Fourier series of function of x, right? So now to get this my constant CR, right? To get my constant CR, what do I need to do? I'll just follow the principle of Fourier series. I say that my constant CR is equal to 2 times the mean value. Remember, the mean value below the function of x. The formula for mean value below the function of x can be written as 1 over L integral comes from 0 to L. Remember, the limit comes from 0 to L, right? Don't forget. From starting of the video, I explained. Remember, the limit comes from 0 to L, meaning that the length of the string 0 to L, right? So the formula for the constant c subscript r is 2 times the mean value from the limit of 0 to L, right, of function of x sine r pi x. Remember, this is just like Fourier series, right? As where we assume this to be Fourier series of fx, so that my CR is equal to this, right? This is just like Fourier series. So we apply the principle of Fourier series here, right? So this is 2 over L. Now, how do we we know we apply the principle of Fourier series? Because remember, for Fourier series, for odd function, we only have sine function in it, right? So I assume this is an odd function, and for odd function, you only have b subscript n. So I assume this is b subscript n, and for b subscript n, this is the formula for finding b subscript n. So technically, we applied Fourier series. So this is 0 to L function of x sine r pi x over L. So this is the formula. So I've gotten my c subscript r. So this is the formula for c subscript r. So what next now is to find the formula for d subscript r, right? So we apply my second boundary condition. Oh, I've stopped counting the steps. So this is my 15 steps, right? Applying my my initial condition. So I apply my first boundary condition. So apply my second boundary condition. Let's call it 15b, right? So apply my second boundary condition, which says du dt, where t is equal to 0, is gx, right? Simple. What we need to do is to differentiate my u. Remember, my u is this, right? So I'm going to be differentiating it. Now, do not worry. Okay, you're asking, so how are we going to differentiate this now when you're having a summation here? You just keep the summation on one side. Remember, I'm differentiating with respect to t, so I can also keep this to one side. And what I'm only concerned with is this function of t here, because I'm differentiating with respect to t. So, let me just write my u. So my u is x, which is a function of x and t. Summation r equals to 1 to infinity, right? This is sine r by x over l, open bracket, cr cos r c by t over l, dot plus d subscript r c by t over l. So, like I said, we're going to be differentiating with respect to t, right? So, what we're only concerned is just the function of t here. So these two here are constant. So I'm just going to be writing it as du dt, right? Du dt, where t is equal to 0, taking this to be constant. So this is sine r pi x over l, summation r equals to 1 to infinity. So I'm only left with du, differentiating this with respect to t, right? Differentiating this here with respect to t. Cr cos RC by t over L plus drc by t over L. So we're going to be integrating this part. So we'll be left with Cr by x over L, this summation r equal to 1 to infinity. So integrating this first one now. So I'm going to be integrating this first one now. So which is Cr. So integrating this is a function of function, this is a function of t. So I'm integrating this one. So I'm multiplying it by this, right? So this r c pi over L cos RC cos. Now when I integrate cos, I'm going to be having sine, right? Sorry, differentiate. When I differentiate cos, I'm going to have a minus sign. So this is minus sine RC pi t over L. So I'm going to do the same thing here also. Remember, this is sine, right? This is a sine function here. There's a sine function here. So I'm going to be doing the same thing here. So doing the same thing here. So that in differentiating sine, I have cos, right? And this is a function here. So let me just write it out if I differentiate it. So this is dr sine RC pi t over L. So when I differentiate this one, I'm going to be having, this is sine r pi x over L, summation r equal to 1 to infinity. So this is minus cr, right, rc pi over L, sine rc pi t over L. So differentiating this one now, this is plus rc pi over L dr cos rc pi t over L. Remember, when I differentiate sine, I have cos, right? So multiplying the function that is in front of the constant, that's multiplying the coefficient of t by what you integrate, what you differentiated. So this is my du dt when t is equal to 0. So I'm going to put in when t is equal to 0 now to get the value of my. Remember, du dt is equal to what? Gx. G is a function of x. So I'm going to put in my t is equal to 0 now to get my g, which is a function of x. So now let's continue. So so substituting when t is equal to 0 into the function. So this is sine r pi x. So now let's call this my step 16. So this is r pi x over L, summation r equal to 1 to infinity. When I put t is equal to 0, this automatically becomes 0 because sine 0 is 0 and 0 times everything is 0. So this is 0 plus, when I put t is equal to 0, this is cos 0 and cos 0 is 1. So it is rc pi over L d prime times 1, right? So so I'm left with, so this is my gx, right? My gx is equal to summation r equal to 1 to infinity x r pi x, or sine r pi x over L, then times rc pi over L dr. Right, so here to also apply Fourier series. So I assume this is an odd function, right? Because I'm only having a sine function here. So since this is an odd function, my my constant here, assume this is b subscript n. My constant, remember, when, if you can remember your Fourier series for odd function, the formula for b subscript n is 2 times the mean value of the area below the function of graph you are constructing. So since this is a constant in front at the back of d, so now let's take this constant to this point. So this is r c pi over l summation r equals to 1 to infinity of dr sine r pi x over l. So if you see that we want to apply if you want to apply the rule of Fourier series to get the answer for d subscript r, we're having an outer constant here, right? So the formula for d subscript r, I'm going to be assigning to d subscript r. I'm going to find a way to eliminate this constant, right? So my d subscript r is going to be equal to 2 times the mean value I'm going to be having is going to be l over r c pi, right? Integral coming from 0 to l of function of x sine r pi x over l. My function of x, remember my function of x is gx. Gx is my function of x. So this r pi x over l dx. So this, my dr, is equal to 2 over r c pi, integral comes from 0 to 1. Sorry, 2 over r c pi. Yeah, 2 over r c pi. Integral comes from 0 to 1. It's going to be 2 over r c pi, and if you remember your mean value usually takes the form of 1 over l. So I think that's what we missed. So my mean value takes the form of 1 over l, right? So I'm going to be having 2 over r c pi. So I'm going to express my function of d in such a way that I'm going to be having 1 over l here. Remember, I have to eliminate this. I have to have just 1 over l, and now to have 1 over l, I'm going to be multiplying it by d 2 over r c pi, right? So since I'm already having 1 over l here, so I just need to cancel out this, right? So cancelling now, so I'm just going to be having 2 over r c pi l, come from 0 to l of g, which is a function of x sine r pi x over l dx. So I think that's that. So what you need to remember when solving sorry, there's no l cancel l, so l cancel l, so I'm just left with rc pi, just rc pi. So which is exactly what we are doing. So in order to cancel this constant out, let me just rephrase my explanation. In order to cancel this function out, I have to assign, just like we did in the first stage, I have to assign 2 over rc pi, just like 2 over rc pi over l. And since my mean value usually takes 1 over l, so l will cancel the l, right? So this, I'm just left with 2 over rc pi. So this is the answer for this is the value of my d subscript r. So we already at the brink to our answer. So now let's just write this function of u. So my function of u, remember, my function of u is written as my general form of u, in which we derived, was summation coming from r equal to 1 to infinity, open bracket, sine r pi x over l, open bracket, c subscript r cos r c pi t over l, plus d subscript r sine r c pi t over l. So now we said, since we've already gotten the value of c subscript r, so we said where c subscript r is equal to 2 over l, it's going to come from 0 to l, right? Pi x sine r pi x over l, and my d subscript r is 2 over r c pi, it's going to come from 0 to l gx sine r pi x over l. So this is how our solution will go. But in most cases, when you're solving a natural problem, we'll just basically skip some steps here, because we just, like I said, we'll skip step 5 to step 7 when solving this. So this is the maximum displacement for the string that's in wave equation. So now you can just take note of this. So now on our next video, we'll be looking at an actual problem on wave equation. So thank you for watching, and please subscribe.